Linear or straight line motion. Objectives: linear motion. Explain how you can tell an object is moving. Describe how you can calculate speed. Distinguish between speed and velocity. Describe how you can calculate acceleration. Describe the acceleration of an object in free fall. Describe how the fall in distance per second changes for an object in free fall. Describe what the slope of a speed versus time graph represents. Describe how air resistance affects the motion of falling objects, and explain the relationship between velocity and acceleration. The big idea. You can describe the motion of objects by its position, speed, and acceleration. More than 2,000 years ago, the ancient Greek scientists were familiar with some of the ideas of physics that we study today. They had a good understanding of some of the properties of light, but they were confused about motion. Great progress in understanding motion occurred with Galileo and his study of balls rolling on inclined planes, as discussed in the previous chapter. In this chapter, we will look at motion in more detail. Discover. Do objects fall faster the longer they fall? Attach washers to a 3.5 meter long string at the following distances from one end: 0 meters, 0.11 meters, 0.44, 0.99, 1.76, etc. Stand on a chair or desk with some string and washer suspended over a piece of metal, such as a pie tin. The washer tied to the end of the string should be touching the metal surface. Release the string and listen to the rate at which the washers hit the metal. You may wish to perform a second trial to confirm your observations. Describe the time interval between sounds. What would you hear if the washers were evenly spaced on the string? What can you say about the distance traveled by a falling object during each second of fall? Something to consider. 4.1. Motion is relative. Everything moves. Everything that appears to be at rest move. They move with respect to the sun and stars. When we describe the motion of one object with respect to another, we say that the object is moving relative to the other object. A book that is at rest relative to the table it lies on is moving at about 30 kilometers per second relative to the sun. The book moves even faster relative to the center of our galaxy. When we discuss the motion of something, we describe its motion relative to something else. An object is moving if its position relative to a fixed point is changing. When we say that a space shuttle moves at 8 kilometers per second, we mean its movement relative to Earth below. When we say a racing car in the Indy 500 reaches a speed of 300 kilometers per hour, of course we mean relative to the track. Unless stated otherwise, when we discuss the speed of things in our environment, we mean speed with respect to the surface of the Earth, even though Earth moves around the sun as shown in figure 4.1. Motion is relative. Figure 4.2, the racing cars in the Indy 500 move relative to the track. Although you may be at rest relative to Earth's surface, you're moving about 100,000 kilometers per hour relative to the sun. A hungry mosquito sees you resting in a hammock in a 3 meter per second breeze. How fast and in what direction should the mosquito fly in order to hover above you for lunch? The mosquito should fly towards you into the breeze. When above you, it should fly 3 meters per second in order to hover at rest above you. Unless its grip on your skin is strong enough after landing, it must continue to fly 3 meters per second to keep from being blown off. That's why a breeze is an effective deterrent to mosquito bites. Concept check. How can you tell if an object is moving? 4.2 Speed. Before the time of Galileo, people described moving things as simply slow or fast. Such descriptions were vague. Galileo is credited as being the first to measure speed by considering the distance covered and the time it takes. Speed is how fast an object is moving. You can calculate the speed of an object by dividing the distance covered by the time. Speed equals distance over time. If a cheetah can maintain a constant speed of 25 meters per second, it will cover 25 meters every second. At this rate, how far will it travel in 10 seconds? In 1 minute. In 10 seconds, the cheetah will cover 250 meters, and in 1 minute, or 60 seconds, it will cover 1,500 meters. For example, if a cheetah, such as the one shown in figure 4.3, covers 50 meters in a time of 2 seconds, its speed is 25 meters per second. Any combination of units for distance and time that are useful and convenient are legitimate for describing speed. Miles per hour, kilometers per hour, centimeters per day, the speed of a sick snail, or light years per century are all legitimate units for speed. The slash symbol is read as per. Throughout this book, we'll primarily use the units meters per second for speed. Table 4.1 shows some comparative speeds in different units. Figure 4.3, a cheetah is the fastest land animal over distances less than 500 meters and can achieve peak speeds of 100 kilometers per hour. You can see how a very good sprinter is only going to be moving 11 meters per second or 25 miles an hour. And you can see that a tsunami is twice the speed of a very good sprinter. So you're not going to outrun much. Humans are not very fast. Instantaneous speed. A car does not always move at the same speed. A car may travel down a street at 50 kilometers per hour, slow to 0 kilometers per hour at a red light, and speed up to only 30 kilometers per hour because of traffic. You can tell the speed of a car at any instant by looking at the car's speedometer, such as the one in figure 4.4. The speed at any instant is called the instantaneous speed. A car traveling at 50 kilometers per hour may go at that speed for only a minute. If the car continued at that speed for a full hour, it would cover 50 kilometers. The speedometer for a North American car gives readings of instantaneous speed in both miles per hour and kilometers per hour. Odometers in the US market give readings in miles. Those in Canada market give readings in kilometers. The center picture is a picture of my moto, and everything is in kilometers per hour, and the odometer is in kilometers. If it continued at that speed for only half an hour, it would cover only half that distance, or 25 kilometers. In a minute, the car would cover less than 1 kilometer. Average speed. In planning a trip by car, the driver often wants to know how long it will take to cover a certain distance. The car will certainly not travel at the same speed all during the trip. The driver cares only about the average speed for the trip as a whole. The average speed is the total distance covered dividing by the time. Average speed equals total distance covered divided by the time interval. Average speed can be calculated rather easily. For example, if we drive a distance of 60 kilometers during a time of 1 hour, we say our average speed is 60 kilometers per hour. Or if we travel 240 kilometers in 4 hours, average speed equals total distance covered divided by time interval. Average speed, 240 kilometers in 4 hours. Average speed is 60 kilometers per hour. 240 divided by 4 is 60. Note that when a distance in kilometers is divided by a time in hours, the answer is in kilometers per hour. Since average speed is the distance covered divided by the time of travel, it does not indicate variations in the speed that may take place during the trip. In practice, we experience a variety of speeds on most trips, so the average speed is often quite different from the instantaneous speed. Whether we talk about average speed or instantaneous speed, we are talking about the rates at which distance is traveled. If we know average speed and travel time, the distance traveled is easy to find. A simple rearrangement of the definition gives distance covered equals average speed times the time travel total. For example, if your average speed is 80 kilometers per hour on a 4-hour trip, then you cover a distance of 300 kilometers. Concept check. How can you calculate speed? The speedometer in every car also has an odometer that records the distance traveled. If the odometer reads 0 at the beginning of a trip and 35 kilometers a half hour later, what is the average speed? The average speed will be the total distance covered divided by the time. 35 kilometers divided by 0.5 hours is 70 kilometers per hour. At some point, the speedometer would have to exceed 70 kilometers per hour. 4.3, velocity. In everyday language, we can use the words speed and velocity interchangeably. In physics, we make a distinction between the two. Very simply, the difference is that velocity is speed in a given direction. When we say a car travels at 60 kilometers per hour, we are specifying its speed. But if we say a car moves 60 kilometers per hour to the north, we are specifying its velocity. Speed is a description of how fast an object moves. Velocity is how fast and in what direction it moves. A quantity such as velocity that specifies its direction as well as magnitude is called a vector quantity. Recall in Chapter 2 that quantities that require only magnitude for a description are scalar quantities. Speed is a scalar quantity. Velocity, like force, is a vector quantity. Constant velocity. Constant speed means steady speed. Something with constant speed doesn't speed up or slow down. Constant velocity, on the other hand, means both constant speed and constant direction. Constant direction is a straight line. The object's path doesn't curve. So constant velocity means motion in a straight line at constant speed. The car in figure 4.5 may have a constant speed, but its velocity is changing. The car on the circular track may have a constant speed, but not a constant velocity because its direction of motion is changing every instant. you can see that the direction is going, right now it might be going to the east, and then it will be going to the south, and then it will be going to the west, and then to the north, etc. Changing velocity. If either the speed or the direction, or both, is changing, then the velocity is changing. Constant speed and constant velocity are not the same. A body may move at constant speed along a curved path, for example, but it does not move with constant velocity because its direction is changing every instant. In a car, there are three controls that are used to change the velocity. One is the gas pedal, which is used to maintain or decrease the speed. The second is the brake, which is used to decrease the speed. The third is the steering wheel, which is used to change the direction. Concept check. How is velocity different from speed? The speedometer of a car moving northward reads 60 kilometers per hour. It passes another car that travels southward at 60 kilometers per hour. Do both cars have the same speed? Do they have the same velocity? Note, velocity is directed speed. Both cars have the same speed, but they have opposite velocities because they are moving in opposite directions. 4.4 Acceleration. We can change the state of motion of an object by changing its speed, its direction of motion, or both. Any of these changes is a change in velocity. Sometimes we are interested in how fast the velocity is changing. A driver on a two-lane road who wants to pass another car would like to be able to speed up and pass in the shortest possible time. Acceleration is the rate at which the velocity is changing. You can calculate the acceleration of an object by dividing the change in its velocity by time. And that's exactly correct. Acceleration equals delta V divided by delta T. Think. Suppose a car moving in a straight line steadily increases its speed each second, first from 35 to 40 kilometers per hour, then from 40 to 45 kilometers per hour, then from 45 to 50 kilometers per hour. What is its acceleration? Notes, can you see that the gas pedal, accelerator, brakes, and steering wheel in an automobile are all controls for acceleration? We see that the speed increases by 5 kilometers per hour during each 1 second interval. The acceleration, therefore, is 5 kilometers per hour dot second during each interval. Acceleration equals change in velocity over time interval. We are familiar with acceleration in an automobile, such as the one shown in figure 4.6. The driver depresses the gas pedal, which is appropriately called the accelerator. The passengers then experience acceleration, or pickup, as it is sometimes called, as they are pressed into their seats. The key idea that defines acceleration is change. Whenever we change our state of motion, we are accelerating. A car that can accelerate well has the ability to change its velocity rapidly. Notes. Mathematics is the language of nature. That's what we do. We convert natural phenomena to mathematical identities to predict outcomes. Figure 4.6, a car is accelerating whenever there is a change in its state of motion. It could be decelerating or accelerating. Both are acceleration. A car that goes from 0 to 60 in 5 seconds has a greater acceleration than another car that goes from 0 to 80 kilometers per hour in 10 seconds. So having good acceleration means being able to change velocity quickly and does not necessarily refer to how fast something is moving. In physics, the term acceleration applies to decreases as well as increases in speed. The brakes of a car can produce large retarding accelerations, that is, they can produce a large decrease per second in speed. This is often called deceleration. We experience deceleration when the driver of a bus or car slams on the brakes and we tend to hurtle forward. Deceleration. Change in direction. Acceleration also applies to changes in direction. If you ride around a curve at a constant speed of 50 kilometers per hour, you feel the effects of acceleration as your body tends to move towards the outside of the curve. You may round the curve at constant speed, but your velocity is not constant because your speed is changing every second. Your state of motion is changing. You are accelerating. It is important to distinguish between speed and velocity. Acceleration is defined as the rate of change in velocity rather than speed. Acceleration, like velocity, is a vector quantity because it is directional. The acceleration vector points in the direction the velocity is changing, as shown in figure 4.7, which is the next slide. When you accelerate in the direction of your velocity, you speed up. Against your velocity, you slow down. At the angle to your velocity, your direction changes. Study this very carefully, very key. If we change speed, direction, or both, we change velocity and we accelerate. Changes in speed. When straight line motion is considered, it is common to use speed and velocity interchangeably. When the direction is not changing, acceleration may be expressed as the rate at which speed changes. Acceleration along a straight line equals change in velocity over time interval. Speed and velocity are measured in units of distance per time. Since acceleration is the change in velocity or speed per time interval, its units are those of speed per time. If we speed up without changing direction from 0 to 10 kilometers per hour in 1 second, our change in speed is 10 kilometers per hour in a time interval of 1 second. Our acceleration along a straight line is acceleration equals 10 kilometers per hour divided by 1 second equals 10 kilometers per hour dot seconds. The acceleration is 10 kilometers per hour per second, which is read as 10 kilometers per hour second, or hour dot second. Same. Note that a unit of time appears twice, once for the unit of speed and again for the interval of time in which the speed is changing. How do you calculate acceleration? Think. In 5 seconds, a car moving in a straight line increases its speed from 50 kilometers per hour to 65 kilometers per hour, while a truck goes from rest to 15 kilometers per hour in a straight line. Which undergoes greater acceleration? What is the acceleration of each vehicle? So, points to ponder. The car and truck both increase their speed by 15 kilometers per hour during the same time interval. So, their acceleration is the same. 4.5, free fall. How fast? An apple falls from a tree. Does it accelerate while falling? We know it starts from a rest position and gains speed as it falls. We know this because it would be safe to catch it if it fell a meter or two, but not if it fell from a high flying balloon. Thus, the apple must gain more speed during the time it drops from a great height than during a shorter time it takes to drop a meter. This gain in speed indicates that the apple does accelerate as it falls. Free fall to a skydiver means fall because the parachute is opened, usually with lots of air resistance. Physics terms and everyday terms often mean different things. Falling objects. Gravity causes the apple to accelerate downward once it begins falling. In real life, air resistance affects the acceleration of a falling object. Let's imagine there is no air resistance and that gravity is the only thing affecting a falling object. An object moving under the influence of the gravitational force only is said to be in free fall. Freely falling objects are affected only by gravity. Table 4.2 shows the instantaneous speed at the end of each second of a fall of a freely falling object dropped from rest. The elapsed time is the time that has elapsed or passed since the beginning of any motion. In this case, the fall. Note in Table 4.2 the way the speed changes. Here's Table 4.2 for your perusal. During each second of fall, the instantaneous speed of the object increases by an additional 10 meters per second. The gain in speed per second is the acceleration. Acceleration equals 10 meters per second, which is 10 meters per second squared. Note that when the change in speed is in meters per second and the time interval is seconds, the acceleration is meters per second squared, which is read as meters per second squared. The unit of time, the second, occurs twice, once for the unit of speed and again for the time interval during which the speed changes. The acceleration of an object in free fall is about 10 meters per second squared. For free fall, it is customary to use the letter g to represent the acceleration because the acceleration is due to gravity. Although g varies slightly in different parts of the world, its average value is nearly 10 meters per second squared. More accurately, g is 9.8 meters per second squared. But it is easier to see the ideas involved when it is rounded to 10 meters per second squared. Where accuracy is important, the value of 9.8 meters per second squared should be used for the acceleration during free fall. Note in figure or in table 4.2 that the instantaneous speed of an object falling from rest is equal to the acceleration multiplied by the amount of time it falls, the elapsed time. Instantaneous speed equals acceleration times time. The instantaneous speed v of an object falling from rest after an elapsed time t can be expressed in the equation form v equals gt. V equals gt. And here is another shot of table 4.2 for your perusal. You can see that each second you're increasing 10 meters per second, as it should be for v equals gt, or 10 times the time interval. Since acceleration is a vector quantity, it's best to say the acceleration due to gravity is 10 meters per second squared down. During the span of the second time interval in table 4.2, the object begins at 10 meters per second and ends at 15 meters per second. What is the average speed of the object during this 1 second interval? What is its acceleration? The average speed will be 15 meters per second. The acceleration will be 10 meters per second squared. The letter V symbolizes both speed and velocity. Take a moment to check this equation with table 4.2. You will see that whenever the acceleration g equals 10 meters per second squared is multiplied by the elapsed time in seconds, the result is the instantaneous speed in meters per second. The average speed of any object moving in a straight line with constant acceleration is calculated the way we find the average of any two numbers. Add them and divide by 2. For example, the average speed of a freely falling object in its first second of fall is the sum of its initial and final speed divided by 2. So adding the initial speed of 0 and the final speed of 10 meters per second and then dividing by 2, we get 5 meters per second. And here is another shot of table 4.2 for your perusal. What would the speedometer reading on the falling rock shown in figure 4.8 be 4.5 seconds after it drops from rest? How about 8 seconds after it is dropped? The speedometer reading would be 45 meters per second and 80 meters per second, respectively. 4.8. If a falling rock were somehow equipped with a speedometer in each succeeding second of fall, its reading would increase by the same amount of 100 meters per second. Table 4.2 shows the speed we would read at various seconds of the fall. Average speed and instantaneous speed are usually very different. In figure 4.8, we imagine a freely falling boulder with a speedometer attached. As the boulder falls, the speedometer shows that the boulder acquires 10 meters per second of speed each second. This 10 meters per second gain each second is the boulder's acceleration. Rising objects. So far, we have been looking at objects moving straight downward due to gravity. Now consider an object thrown straight up. It continues to move upward for a while, then it comes back down at the highest point. When the object is changing its direction of motion from upward to downward, its spontaneous speed is 0. It then starts downward just as if it had been dropped from rest at that height. Here's 4.8 once again for your perusal, and here's table 4.2 again for your perusal. During the upward part of this motion, the object slows from its initial upward velocity to 0 velocity. We know the object is accelerating because its velocity is changing. How much does its speed decrease each second? It should come to no surprise that the speed decreases at the same rate it increases when moving downward, at 10 meters per second each second. So, as figure 4.9 shows, the instantaneous speed at points of equal elevation in the path is the same whether the object is moving upward or downward. The velocities are different, of course, because they are in opposite directions. Figure 4.9. The change in speed each second is the same whether the ball is going up, the speed would decrease, or down, increase. During each second, the speed or velocity changes 10 meters per second. The acceleration is 10 meters per second squared downward the entire time, whether the object is moving upward or downward. Discover, can you catch a falling bill? Have a friend hold a dollar bill in the midpoint hangs between your fingers. Have your friend release the bill without warning. Try to catch it. Think. How much reaction time do you have when your friend drops the bill? 4.6, free fall. How far? How fast something moves is entirely different from how far it moves. Speed and distance are not the same thing. To understand the difference, we turn to Table 4.2. At the end of the first second, the falling object has an instantaneous speed of 10 meters per second. Does this mean it falls a distance of 10 meters during the first second? No. Here's where the difference between instantaneous speed and average speed comes in. The initial speed of fall is 0 and takes a full second to get to 10 meters per second. So the average speed is halfway between 0 and 10 meters per second. That's 5 meters per second, as discussed earlier. Here is figure 4.10 for your perusal again. Look at it carefully. So during the first second, the object has an average speed of 5 meters per second and falls a distance of 5 meters. Table 4.3 shows the total difference moved by a freely falling object dropped from rest. At the end of 1 second, it has fallen 5 meters. At the end of 2 seconds, it has dropped 20 meters. At the end of 3 seconds, it has dropped 45 meters altogether. For each second of free fall, an object falls a greater distance than it did in the previous second. Table 4.3, free fall distances of an object. Here you have the x-axis, or the horizontal axis. You have elapsed time, and then the fallen distance. So on the next slide, you'll see the graph. So peruse these carefully, and then look at the graph and see if a graph is the same. You can see the picture, the freeze frame picture, where the distance the ball is going each time frame increases. And here is 4.12, a distance versus time graph of the data from table 4.3. And you can see very clearly that it is parabolic. These distances form a mathematical pattern at the end of time t. The object has fallen a distance d of 1/2 gt squared. We used freely falling objects to describe the relationship between distance traveled, acceleration, and velocity acquired. In our examples, we use the acceleration of gravity, g equals 10 meters per second squared. But accelerating objects need not be freely falling objects. A car accelerates when we step on the gas or the brake pedal. Think, an apple drops from a tree and hits the ground in 1 second. What is the speed upon striking the ground? What is the average speed during 1 second? How high above the ground was the apple when it was first dropped? When it hits the ground, the apple's speed will be 5 meters per second. Its average speed is 5 meters per second, and it starts 5 meters above the ground. Whenever an object's initial speed is 0 and the acceleration a is constant, that is, steady and non-jerky, the equations for the acceleration and distance traveled are v equals at and d equals 1/2 gt squared, where g could be a, but that's for a freely falling object. For a freely falling object, how does the distance per second change? 4.7, graphs of motion. Equations and tables are not the only way to describe relationships such as velocity and acceleration. Another way to use the graphs that visually describe relationships. Since you since you'll develop basic graphing skills in the laboratory, we won't make a big deal of graphs. Here, we'll simply show the graphs for table 4.2 and 4.3, speed versus time. Figure 4.11 is a graph of the speed versus time data in table 4.2. Note the speed v is plotted on the vertical axis and t time is plotted on the horizontal axis. In this case, the curve, quote unquote curve, that best fits the data forms a straight line. So the first relationship is very linear. There's the graph of there's the data table. You've seen it before. And now the graph. And there's the graph, speed versus time. Speed on the y-axis and time on the x-axis. The straightness of the curve indicates a linear relationship between speed and time. For every increase of 1 second, there is the same 10 meters per second increase in speed. Mathematicians call this linearity, and the graph shows why. The curve is a straight line. Since the object has dropped from rest, the line starts at the origin, where both v and t are 0. If we double t, we double v. If we triple t, we triple v, and so on. This particular linearity is called a direct proportion, and we say that time and speed are directly proportional to each other. The curve is a straight line, so its slope is constant, like an inclined plane. Slope is the vertical change divided by the horizontal change for any part of the line. Note, the slope of a line on a graph is rise over run, or the change in y divided by the change in x, or the change in velocity divided by the change in time. So the slope of the line of a velocity time graph would be the acceleration. On a speed versus time graph, the slope represents speed per time or acceleration. Note that for each 10 meters per second of vertical change, there is a corresponding horizontal change of 1 second. We see the slope is 10 meters per second divided by 1 second, or 10 meters per second squared. The straight line shows the acceleration is constant. If the acceleration were greater, the slope of the graph would be steeper. For more information about slope, see Appendix C. Distance versus time. Figure 4.12 is a graph of distance versus time data in table 4.3. Distance d is plotted on the vertical axis and time t is on the horizontal axis. The result is a curved line. The curve shows that the relation between distance traveled and time is nonlinear. The relation shown here is quadratic, and the curve is parabolic. When we double t, we do not double d, we quadruple it. Distance depends on time squared. A curved line also has a slope. Different at different points. If you look at the graph of figure 4.12, you can see that the curve has a certain slant or steepness at every point. And there is the graph that we speak of. Again, I showed the graph before just to show you how the data from table 4.3, how that is represented in graphical form. This slope changes from one point to the next. The slope of the curve on the distance versus time graph is very significant. It is speed, the rate at which distance is covered per unit time. In this graph, the slope steepens, becomes greater as time passes. This shows that speed increases as time passes. In fact, if the slope could be measured accurately, you would find it increases by 10 meters per second each second. Concept check. What does a slope of a speed versus time graph represent? 4.8, air resistance and falling objects. Drop a feather and a coin, and we notice the coin reaches the floor far ahead of the feather. Air resistance is responsible for these different accelerations. This fact can be shown quite nicely with a closed glass tube connected to a vacuum pump. The feather and the coin are placed inside. When the tube is inverted with air inside, the coin falls more rapidly than the feather. The feather flutters through the air, but if the air is removed with a vacuum pump and the tube is quickly inverted, the feather and the coin fall side by side with the same acceleration g as shown in figure 4.13. Here is figure 4.13. A feather and a coin accelerate equally when there is no air around them. Air resistance noticeably slows the motion of things with large surface areas like falling feathers or pieces of paper, but air resistance less noticeably affects the motion of more compact objects like stones and baseballs. In many cases, the effect of air resistance is small enough to be neglected. With negligible air resistance, falling objects can be considered to be falling freely. Air resistance will be covered in more detail in Chapter 6. How fast something falls is entirely different from how far it falls. From rest, how fast is given by v equals gt, and how far, d equals 1/2 gt squared. How does air resistance affect falling objects? That's the concept check. How fast, how far, how quickly, how fast changes. Some of the confusion that occurs in analyzing the motion of falling objects comes from mixing up how fast with how far. When we wish to specify how fast something freely falls from rest after a certain elapsed time, we're talking about speed or velocity. The appropriate equation is v equals gt. When we wish to specify how far that object has fallen, we're talking about distance. The appropriate equation would be d equals 1/2 gt squared. Velocity or speed, how fast, and distance, how far, are entirely different from each other. One of the most confusing concepts encountered in this book is acceleration, or how quickly speed does change or velocity change. What makes acceleration so complex is that it is a rate of a rate. It is often confused with velocity, which is itself a rate, the rate at which distance is covered. Acceleration is not velocity, nor is it even a change in velocity. Acceleration is the rate at which velocity itself changes. Worth repeating, acceleration is the rate at which velocity itself changes. Please be patient with yourself if you find that you require several hours to achieve a clear understanding of motion. It took people 2,000 years from the time of Aristotle to Galileo to achieve as much. What is the relationship between velocity and acceleration? Now let's look at hang time. Some people are gifted with great jumping ability. Leaping straight up, they seem to hang in the air. Ask your friends to estimate hang time of the great jumpers, the amount of time a jumper is airborne, feet off the ground. 1 or 2 seconds? Several? Nope. When I used to watch Michael Jordan, it literally looked like he was up there for, half a minute. It was unbelievable how he just flew through the air. Surprisingly, the hang time of the greatest jumpers is almost always less than 1 second. Our perception of a longer hang time is one of the many illusions we have about nature. Jumping ability is best measured by a standing vertical jump. Stand facing a wall and with feet flat on the floor and arms extended upward, make a mark on the wall at the top of your reach. Then make your jump, and at the peak, make another mark. The distance between these two marks measure your vertical leap. Here's the physics. When you leap upward, jumping force is applied only as long as your feet are still in contact with the ground. The greater the force, the greater your launch speed, and the higher the jump is. It is important to note that as soon as your feet leave the ground, whatever upward speed you attain immediately decreases at the steady rate of 10 meters per second squared. Maximum height is attained when your upward speed decreases to 0. You then begin falling, gaining speed at exactly the same rate g. If you land as you took off upright with legs extended, then time rising equals time falling. Hang time is the sum of the rising and falling times. The relationship between rising and falling time and vertical height is given by d equals 1/2 gt squared. If you know the vertical height, we can rearrange this expression to read t equals root 2d over g. No basketball player is known to have exceeded a jump of 1.25 meters, 4 feet. Setting d equal to 1.25 meters and using the more precise 10 meters per second squared for g, we find that t, half the hang time is, equal to 0.5 seconds. Doubling this, we see such a record hang time would be 1 second. We've only been talking about vertical motion. How about running jumps? We'll learn in Chapter 5 that hang time depends only on the runner's vertical speed at launch. It does not depend on horizontal speed. While airborne, the jumper's horizontal speed remains constant, but the vertical speed undergoes acceleration. Interesting physics. Notes: hang time can be several seconds in the sport of sail surfing, quite a bit different when the air plays a major role. Summary: an object is moving if its position relative to a fixed point is changing. You can calculate the speed of an object by dividing the distance covered by time. Speed is a description of how fast an object moves. Velocity is how fast and in what direction it moves. You can calculate the acceleration of an object by dividing the change in its velocity by time. The acceleration of an object in free fall is about 10 meters per second squared, or 10 meters per second squared. For each second of free fall, an object falls a greater distance than it did in the previous second. On a speed versus time graph, the slope represents speed per time, or acceleration. Air resistance noticeably slows the motion of things with large surface areas like falling feathers or pieces of paper. But air resistance less noticeably affects the motion of more compact objects like stones and baseballs. Acceleration is the rate at which velocity itself changes.